Since the dawn of humanity, the moon has been a source of wonder and inspiration, and was a symbol of the unreachable, the distant companion of the night sky. Humanity's quest to explore and understand this celestial body has been marked by significant milestones, each one a stepping stone towards the future. In 1957, the Soviet Union launched Sputnik, the first artificial satellite uniting the space race. This was a monumental achievement, but it was just the beginning. The challenge was set, and the world watched as humanity reached for the stars.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
With these words, President Kennedy set the stage for one of the most ambitious endeavors in human history. The Apollo missions would soon follow, pushing the boundaries of what was possible. On July 20, 1969, the Apollo 11 mission successfully landed the first humans on the moon. Neil Armstrong's historic words, "It's one small step for man, one giant leap for mankind," echoed around the globe, symbolizing the triumph of humanity and determination. The Apollo program continued to explore the lunar surface, conducting vital scientific research and collecting samples that would deepen our understanding of the moon and its history. These missions laid groundwork for future exploration, proving that humanity could reach beyond our home planet. As technology advanced, so did our methods of exploration. Robotic missions such as the Lunar Reconnaissance Orbiter and the Chinese CADRE program provide detailed maps and insights into the moon's composition, paving the way for new discoveries. Today, we stand on the brink of a new era in lunar exploration with NASA's Artemis program, aiming to return humans to the moon and establish a sustainable presence. These efforts are crucial stepping stones for our ultimate goal, Mars and beyond. And now, NASA introduced the CADRE mission, Cooperative, Autonomous, Distributed Robotic Exploration. Set to launch in 2024, this mission will deploy a network of small autonomous rovers to collaboratively explore the moon's surface. These rovers represent the pinnacle of modern technology, capable of performing complex tasks without direct human intervention, and pave the way for future multi-robot missions. The journey from the early days of the space race to the innovative CADRE mission showcases the incredible progress in lunar exploration. Each mission, each technological advancement has brought us closer to understanding our nearest celestial neighbor. This is the story of human ingenuity, perseverance, and the relentless quest to uncover the mysterious of the moon. From Apollo to CADRE, a new era of lunar exploration. The CADRE mission, short for Cooperative Autonomous Distributed Robotic Exploration, is set to launch in 2024. Its primary goal is to demonstrate the potential of autonomous, cooperative robotic systems in space exploration. A trio of small rovers will work as a team to explore the moon autonomously, mapping the subsurface in 3D, collecting distributed measurements, and showcasing the potential of multi-robot missions. The centerpiece of this mission are 3 small rovers, each about the size of a carry-on suitcase. These rovers are equipped with solar panels, stereo cameras, navigation sensors, and multi-static ground-penetrating radar. They will work together to explore the moon's surface, particularly targeting the Rhina Gamma region. The Rhina Gamma is a geographical feature of the moon, known as a lunar swirl. It is one of the most visible lunar swirls from Earth. Located in the Oceanus Procellarum on the near side of the moon, the Rhina Gamma region stands out as a distinctive feature on the lunar surface. This bright, sweeping swirl contrasts sharply with the darker surrounding terrain, extending over several hundred kilometers. Unlike many other lunar features, Rhina Gamma was not formed by impacts or volcanic activity. But what are lunar swirls? Lunar swirls are bright, often curving patterns on the moon's surface that resemble abstract paintings. One of the key factors behind these swirls is the presence of local magnetic fields on the moon's surface. These magnetic fields act like a neutral sunscreen, shielding specific areas from the solar wind. The effect of the solar wind on the lunar surface is profound. In areas not protected by magnetic fields, the solar wind induces chemical reactions that darken the surface. However, in the shielded regions, these reactions are minimized, allowing the surface to remain brighter. For further investigations and understanding of these intriguing lunar swirls and the broader mysterious of the Moon's surface, advanced research and technological innovation are essential. This crucial work is undertaken by NASA's Jet Propulsion Laboratory, commonly known as JPL. Located in Southern California, JPL is a leader in the field of robotic space exploration. Federally founded by NASA and managed by Caltech, JPL has a rich history of groundbreaking missions and is instrumental in developing the technologies that enable ambitious projects like the CADRE mission. Integral to the success of the CADRE mission is the transportation and deployment of its rovers on the lunar surface. This critical responsibility is entrusted to the IM-3 lander, developed by Intuitive Machines. IM-3 is part of NASA's Commercial Lunar Payload Services initiative, in which NASA contracts with a commercial partner, in this case Intuitive Machines, to provide the launch and lander services. The main component of IM-3 is the Nova C lander, a tall hexagonal cylinder on 6 landing legs. Capable of carrying 100 to 130 kilograms of payload to the surface, it will transport 4 NASA payloads to the Rhine-Gammon region of the Moon, including the CADRE rovers. Its launch is planned on the Falcon 9. Upon arrival on the Moon, the 3 rovers will communicate with each other via mesh network radios and the base station aboard the lunar lander. The rovers will operate mostly autonomously, making decisions and taking actions without the need for constant human intervention. The network of robots will utilize the daylight hours of a lunar day, equivalent to approximately 14 Earth days, to conduct experiments designed to rigorously test their capabilities. The CADRE mission represents a significant leap forward in the field of robotic space exploration. By integrating cutting-edge technologies and innovative approaches, this mission aims to demonstrate the full potential of autonomous, cooperative robotic systems. By collecting measurements simultaneously from various locations, the rovers will showcase the ability of multiple robots to collaboratively gather data that a single robot could not achieve alone. Their success could pave the way for autonomous multi-robot missions to pursue scientific objectives through distributed measurements, navigate researchers in uncharted terrain, or assist astronaut activities. The system is designed to allow agents, rover and the base station to share data within the team and make collaborative decisions on task execution. The rovers will autonomously travel information and working together to explore the local lunar surface. They will generate a digital elevation map and perform distributed measurements using their micro payloads. The manager of the CADRE project at NASA's Jet Propulsion Laboratory, Subhak Mander, said, "Our mission is to demonstrate that the network of mobile robots can cooperate to accomplish a task without human intervention, autonomously. It could change how we do exploration in the future. The question for future missions will become, how many rovers do we send and what will they do together?" CADRE's principal investigator, Jean-Pierre Delacroix, added, "The only instruction is, for example, go explore this region and the rovers figure out everything else. When they'll do the driving, what path they'll take, how they'll maneuver around local hazards. You only tell them the high-level goal, and they have to determine how to accomplish it." Monitored by a camera atop the 30-foot-tall lander, the rovers will execute their tasks. These tasks include driving information and navigating around obstacles, with each rover exploring a section of the lunar surface spanning 4,300 square feet. Utilizing stereo cameras, they will create a detailed 3D topographic map. Additionally, the rovers are equipped with ground-penetrating radars capable of probing up to 33 feet beneath the surface. While driving information, each rover will detect the reflections of radio signals transmitted by the others, thereby generating a 3D image of the subsurface structure up to 33 feet deep. Collectively, they can gather more comprehensive data than the current state-of-the-art ground-penetrating radars, such as the Radar Imager of Mars Subsurface experiment on NASA's Perseverance Mars rover. While there are numerous scenarios designed to test the full extent of the CADRE rover's autonomy and teamwork capabilities, including surviving the harsh thermal environment near the Moon's equator and monitoring the longevity of the GPL-developed cooperative autonomy software using a combination of commercial off-the-shelf parts and custom-built components, the primary goal is to determine whether the rovers are robust enough to make it through their trial period relatively unscathed. Mission controllers on Earth will send general directives to the rover's base station aboard the lander. From these initial instructions, the rovers are programmed to elect the leader, which in turn will distribute work assignments to accomplish the collective goal. Each rover will independently determine the best way to safely complete its assigned task. The project will also assess how well the team would adapt if a rover stopped working for some reason. And not just that, they look out for each other too. When one rover runs low on juice in its solar batteries, the other two rovers wait for the companion solar array to recharge before continuing together. Commander said, "We have been in overdrive getting this tech demo ready for its lunar adventure. It's been months of nearly round-the-clock testing and sometimes retesting, but the team's hard work is paying off. Now we know these rovers are ready to show what a team of little space robots can accomplish together." After the mission, CADRE intends to make the software stack and hardware designs available under a free license within the US, aiming to foster innovation and promote autonomous exploration of the Moon and beyond. One of the central aspects of the mission is the navigation of the rovers, including mapping and obstacle detection. The CADRE rovers use an advanced navigation map optimized for autonomous mobile robots operating in unknown environments. By using a new method called Converging Covariance Mapping, short CCM, the rovers can effectively detect hazards like obstacles and steep slopes and targets a collision-free operation. This approach is more efficient than traditional methods because it identifies small obstacles and terrain changes in great detail without needing heavy computation. It works well with stereo vision systems that have short baselines and low viewpoints, making it ideal for robots with limited computing power. A cell is a small area within the entire mapping area. This method resolves subcell obstacles and terrain gradients at the individual cell level, so not like a traditional window-based hazard analysis. It avoids the computational overhead and leverages a multi-resolution strategy adaptive to the range errors common in stereo vision systems, which means that the data is now analyzed and processed at different levels of detail. Despite the increased precision, the method is more efficient and requires less computing power than conventional methods, making it ideal for embedded systems. So to summarize, the functionality includes constant type queries for height, obstacle presence and slope details, offering improvements in runtime, memory usage, precision, and the ability to detect smaller obstacles compared to existing grid-based mapping algorithms. In the following, we will go through the various steps that make up converging covariance mapping, which are very important for understanding the method. First, a few fundamental aspects should be explained. The CADRE mission uses short baseline stereo imaging at an oblique ground-near angle, producing a point cloud with uneven point density and measurement noise. High-density, low-noise data near the robot is analyzed for small obstacles, while less precise data from further away identifies larger obstacles for long-term planning. Multi-layer maps with different sizes and resolutions are used to overcome this issue and adjust the sensor resolution in the map architecture. Various mapping techniques for each layer are employed to optimally utilize the available information and computational resources. This method uses an incremental update for each cell to estimate the local inclination and the intracell roughness. In addition, the method enables the detection of obstacles that are smaller than the resolution of the map. Let's take a closer look at one cell. The height measurements within a cell are influenced by both the sensor's measurement variance and the terrain variance caused by surface irregularities. The measurement variance is the variance caused by the inaccuracy of the sensor. Each sensor has a certain measurement accuracy, and the measured altitude values can vary due to measurement noise or other uncertainties. The terrain variance is the variance caused by the irregularities of the terrain surface. The terrain within a cell is rarely perfectly flat, and these natural irregularities contribute to the overall variance of the elevation values. These two variances, the measurement uncertainty of the sensor and the terrain variance, combine to create the sample variance in each cell. The sample variance is a measure of how much the height values within the cell scatter around their mean value. To improve evaluations, it is advantageous to estimate the full three-dimensional sample distribution. 5 specific elements from the three-dimensional covariance matrix are required for each cell. These elements describe the variances along the three spatial axes and the covariances between the lateral and vertical axes. In addition to the covariance values, the three-dimensional mean value of the measurements and the cumulative weighting factor must also be recorded for each cell. The weighting factor makes it possible to compensate for unevenly distributed measurements and to take into account the influence of each measurement on the calculation of the covariances. Therefore, a total of 9 values are stored for each cell. An incremental update step is used so that the entire map does not have to be completely recalculated in each step. Certain update equations make it possible to integrate new measurements into the existing map model, which is particularly important for real-time applications where fast and continuous updates are required. Weighting the measurements ensures that new data is appropriately considered, while the variance and covariance calculations capture the dispersion and common variations of the data within the cell. The objective in this step is to move from the a priori state to the posteriori state using a single point measurement. Before updating, the respective cell must be identified by discretizing the map, whereby the measured coordinates at the cell center point play an important role. First, we have to update the weight by adding a constant value, which has been proven to be sufficient in tested configurations. The measurement weight determines the influence of the new data compared to the existing data. This weight is derived from the sensor model and is a crucial parameter of the map. Furthermore, deviation of the measurement from the cell center is calculated, which is necessary for the following calculation. The next step is to update the mean value of the cell center, followed by updating the variance and covariance. To ensure consistent significance of new measurements in the incremental update, a convergence limiter is implemented. This limiter activates when the accumulated weight exceeds a specific threshold. In this case, the variance and covariance are assigned specific weighting again. This limitation ensures that the importance of new measurements does not decrease even if the number of measurements increases. And now the next step is map theory. A map theory in the CCM provides the mean height of a cell, the inclination along two axes, and the variance of the surface normal, making it possible to perform height and inclination estimates at the subcell level. The calculated values from the incremental update step can now be used to calculate the new values in the map theory step. Now we have the height and inclinations, or the overall inclination, which are crucial metrics for assessing the passability. The threshold used to determine whether a variance is high enough to indicate an obstacle is established through simulations. In these simulations, an obstacle with the minimum detectable height is placed within the cell and the resulting surface normal variance is calculated. The simulations compute the surface normal variance for different levels of obstacle coverage within a cell. This figure shows the resulting variance values for cells with a width of 32 cm, where the obstacle occupies 75% of the cell width. A threshold based on 50% cell coverage allows the detection of obstacles covering between 11% and 91% of the cell. The next important step is pooling. Pooling is a strategy designed to significantly reduce computational effort on multi-layer, multi-size mapping algorithms. It allows new measurements to be integrated only at the highest available resolution, eliminating the need to update all layers simultaneously. The lower resolution layers are updated only during query time by merging higher resolution cells. However, because individual CCM cells estimate different distributions with unique means and covariances, they cannot be merged into a single unit using conventional methods. Standard approaches for mixtures of Gaussian distributions, which assume all measurements observe a uniform value, are not applicable in this context. The mean value of the new, lower resolution cell is calculated as the average of the mean values of the higher resolution cells. The variance of the new cell is calculated by the average of the variances of the higher resolution cells, in addition to taking into account the quadratic deviation between the mean values. The covariance is calculated in a similar way to the variance, but the cross-correlation between the mean values of the different axes is taken into account. We now have almost all the information we need to understand CCM. What is still missing is a method to decide how big the cells, which I've been talking about all this time, should be. This is necessary to ensure that the variance induced by terrain features exceeds the variance caused by measurement noise, which is ensured by comparing the measurement standard deviation and the anticipated standard deviation of a uniform distribution of cell dimensions, defines as sigma r equals root of w squared divided by 12, where w denotes the cell width. For CCM to accurately converge to the terrain values must be at least twice as large as the measurement standard deviation to effectively filter out range noise. As a result, this sets a lower limit on the cell size for a given distance and sensor model. The comparison with traditional methods utilizing piecewise constant elevation maps shows a clear difference. The converging covariance map algorithm presents several distinct advantages over traditional mapping methods, making it a superior choice for applications in autonomous robotic navigation and exploration, such as those undertaken by the CADRE mission. The converging covariance map is a highly effective tool for estimating both the height and slope of terrain, making it an ideal solution for mobile robotic platforms with limited computational resources that need accurate slope and hazard data for safe operations. It surpasses traditional methods that use piecewise constant elevation maps in terms of precision while using similar computational resources. To illustrate an example, here's a simulation comparing the accuracy of the CCM method with the OMG update and CADRE methods. In a test with 3-meter resolution, the elevation arrow plots clearly show the absolute differences between actual and estimated elevations, revealing finer details at the subcell level. This highlights the discrepancy between piecewise linear and constant mapping techniques. Both Kalman and OMG updates produce identical elevation arrow maps and total root mean square arrows due to their similar elevation estimation processes. However, the CCM map shows significantly lower arrows in individual cells, resulting in a lower overall elevation construction error. Further tests on variance accuracy, obstacle detection capability, map performance across various lunar terrains, paths and obstacle sizes, as well as depth and noise evaluation, cell classifications in relation to the actual presence of obstacles, drift resilience, real-world tests and more illustrate the advantages over traditional methods. Despite limitations in terms of depth errors at object boundaries and associational misclassification, these tests demonstrate that the CCM method is not only significantly better suited for the CADRE mission, but also paves the way for future advancements in autonomous robotic exploration, ensuring safer and more efficient navigation in uncharted extraterrestrial environments. The testing of the rover has focused on 2 main areas. The first one is evaluating how well CADRE's cooperative autonomous software functions by driving demonstration models of the rovers around GPL's Martial, which is an outdoor obstacle course for rovers, now a lunar terrain simulator as well. Another aspect of the testing involved preparing the rovers for the intense conditions of launch in the harsh lunar environment, where extreme temperature fluctuations and varying light and shadow could impact their performance. Specifically, mission engineers have adopted a shake and bake strategy. The shake involves securing the rovers to a shaker table that mimics the intense vibrations they will endure during their launch aboard a SpaceX Falcon 9 rocket. The bake entails placing the rovers in a thermal vacuum chamber which alternates between high heat and freezing conditions to replicate the extreme temperatures of space. "The tests are incredibly nerve-wracking to witness in person," said CADRE Project's Flight System Manager Guy Sogar. "After all, any mistake during testing could undo the extensive effort that went into building the rovers if they get damaged or destroyed. Fortunately, each test has ultimately been successful," Sogar added. These examinations haven't been limited to the rovers alone. All the supporting hardware destined for the Moon or intuitive machines on the Sea Lander has undergone testing as well. This includes a base station for rover communication, a camera to monitor the rover's activities, and a motorized spool that will deploy the rovers onto the lunar surface via an unwinding fiber tether. And what's next? Now that testing is complete, the rovers and their hardware are being shipped off to intuitive machines in Houston, where they will be mated to their Nova Sea Lander. After that, the Falcon 9 rocket will launch with the Nova Sea Lander, including the CADRE payload, marking the beginning of the mission. The CADRE mission represents a groundbreaking step forward in the field of autonomous robotic space exploration. Scheduled for launch in 2024, CADRE aims to demonstrate the capabilities of a network of small autonomous rovers that can collaboratively explore the lunar surface. By utilizing advanced technologies such as the converging covariance map algorithm, these rovers are equipped to perform detailed mapping and hazard detection in real time, ensuring safe and efficient navigation across the Moon's rugged terrain. One of the primary goals of the CADRE mission is to showcase the effectiveness of multi-robot systems in conducting simultaneous measurements from different locations. This approach enables the collection of data that a single robot could not gather, thereby significantly enhancing the scope and accuracy of scientific observations. The success of this mission could pave the way for more sophisticated multi-robot missions in the future, capable of pursuing complex scientific goals, navigating hazardous and unexplored terrains, and providing critical support for astronaut activities. The innovative CCM algorithm central to the CADRE mission offers numerous advantages over traditional mapping methods. By providing highly accurate estimates of both height and slope, CCM ensures that the rovers can detect and avoid obstacles with unprecedented precision. This capability is crucial for missions that require high levels of autonomy, as it minimizes the need for human intervention and allows the rovers to operate effectively in remote and challenging environments. Looking to the future, the technologies and methodologies developed for the CADRE mission have the potential to revolutionize space exploration. The ability to deploy networks of autonomous robots that can work together seamlessly opens up new possibilities for the exploration of other celestial bodies, including Mars. These advancements will not only enhance our scientific understanding of these environments, but also support the establishment of sustainable human presence beyond Earth. Furthermore, the success of CADRE will likely influence the development of autonomous systems for terrestrial applications. Innovations in navigation algorithms, sensor integration, and multi-robot coordination can be adapted for use in various industries, including search and rescue operations, environmental monitoring, and automated transportation systems. In summary, the CADRE mission is set to make significant contributions to the field of autonomous robot exploration. Its pioneering use of cooperative multi-robot systems and advanced mapping technologies will provide valuable insights and pave the way for future missions, both in space and on Earth. As we continue to push the boundaries of what is possible, the lessons learned from CADRE will play a crucial role in shaping the next era of exploration and discovery. The technological journey from the first manned moon landing in 1969 to the CADRE mission of today is a testament to the remarkable advancements in space exploration. The Apollo missions laid the foundation, demonstrating the feasibility of lunar exploration and human spaceflight. Over the decades, technological innovations have transformed our capabilities, from the development of sophisticated robotics and AI to advancements in material science and militarization of instruments. These innovations have enabled the creation of highly autonomous systems capable of performing complex tasks with minimal human intervention. The CADRE mission embodies one of the combination of these advancements, showcasing how far we come in our quest to explore and understand the cosmos.